In this section, we're going to discuss merge sort, an improvement over selection and insertion sorting. Selection and insertion sorts are easy to understand and implement, but their runtime cost is high. It's the order n squared. This means for large data sets, say 1,000,000 elements, the runtime cost is something on the order of 1,000,000 times 1,000,000 operations. That's a lot. Some computers would not finish that in a reasonable amount of time. We would consider it a non-viable solution. In commercial and academic applications, that simply wouldn't work. Merge sort was developed to reduce the runtime cost to a more manageable big O n log n. The cost of 10 to the sixth elements, 1,000,000, is about 20 times 10 to the sixth, or 20 million costly operations. Far better than 10 to the 12th power. The logic behind a merge sort more complicated and may take a try or two to understand, but that's okay. It's a more clever scheme and it's based upon recursion. And like the binary search, this sort routine recursively divides a list of elements into halves and sorts each of those halves independently. Well, in a sense, the merge sort never sorts, oddly enough. It keeps dividing the data into halves until there's one element in each half. Now, by definition, one element is sorted because it is the only element. So we never actually get around to sorting in a technical sense. Once the data is down to single elements in each list, we then merge the lists together. This is where technically the sorting occurs. We have at the lowest level two lists to merge, each with one element. The merge then simply decides which is the smallest element and merges it first, and then it chooses the largest element second. So now we have a list of two elements in sort order. Well, that occurs at every point where we have a list of one element on the left and one element on the right. We merge and come up with a list of two elements in sorted order. And that continues back up. Whereas we divided the data into halves, we're now recombining the data. Those halves get joined into units. So at the first level, we have two individual elements joining into two. And then the next level, we have two sets of two elements each merging into a set of four elements, on and on upward, until finally we have the final list. This approach allows us to subdivide the original set of data into multiple pieces. Ultimately, we wind up with n elements, n lists of single elements, and then merging. But to get to that level, we took log n divisions of the data in the halves. The return, where we merge elements together, takes log n steps to go from single elements back up to a full list. At each level, we must manipulate n elements. So the ultimate big O notation here is n, that's the number of elements, times log n, which is the number of levels that we divided in half each time and then rejoined by doubling and coming back up. So the runtime, as has been noted, is a lot faster than n squared. It's just getting the details in your mind correctly that's hard. The result is that this more clever algorithm runs vastly faster on large data sets. To understand this algorithm, it probably would help to sit down with a piece of paper and a pencil and draw out a list of 8 or 10 elements and do the steps. Divide the list in half, and each of those halves divide in half again until you get down to single elements, merge them together, and go back up. And you will notice that the subdividing of the list occurs log n time. The merging handles n elements every level, so the final result is our big O, n times log n. This algorithm really brings to bear the trade-off of effort at a human cost versus the cost of the machine running. One usually dominates, and that's the one you optimize for. If the effort costs more than the benefit, then we use a very simple algorithm. We don't want our programmers spending long amounts of time coding and testing for just a small benefit. However, if the data is large enough, then the programmer cost becomes minimal and we choose to optimize for performance. And this is where a merge sort or a Q sort, quick sort, which is another recursive algorithm, come in handy. Many companies have made a lot of money by making fast, optimized search and sort routines. Big businesses, government, academic institutions need that. So there's a lot of benefit into studying and knowing how to choose the best algorithm at the right time.